All right, good afternoon, everyone, and welcome to the lecture 9 of our course on quantum computing. And today we're gonna dive into quantum teleportation algorithm and start discussing Grover search algorithm with more detailed discussion next week. But before we start, let me quickly repeat what we have discussed last week, the last lecture. So last time we've discussed the basics, the basic and golden quantum circuits, and discussed the Python library called Qiskit, which we use for quantum simulations, right? So what is important point here, so we discussed the general workflow with the Qiskit, including the creation of the circuit, the quantum circuit, the adding of qubits, the qubits and gates to the circuit, and the way how we can operate with the states, like how we can give any state to the circuit of interest, and how we can compute the result of acting this circuit on the state, right? So in this way, Qiskit is we can use Qiskit as a calculation mean, similar to SymPy quantum. So important type of circuits that we discussed first was 2-qubit golden quantum circuit, which we introduced even before, but last time we discussed in more detail how it works and why we need such type of circuit. So we need this circuit basically to create the entangled state of 2 qubits. This is the operation that we significantly need, for example, for quantum teleportation that we will discuss today. We discussed the representation of the state of the quantum system by this Q-sphere representation. We discussed the difference of the Q-sphere comparing to the block sphere. So again, block sphere describes the state of one single qubit. Q-sphere is the generalization of block sphere to a large number of qubits. Generalization of the golden 2-qubit circuit is the circuit generating GHZ state or Greenberg-Horn-Zelenberg state. And for example, for a system of 3 qubits, it looks like this. So you basically entangle 3 qubits, and the resulting state looks like this. Again, this is inseparable state. And if you measure any qubit in this system, it will immediately affect the state of others, or statistics, the distribution of possible states over other qubits in the system. We discussed how to introduce measurement and how we can simulate measurement using the Qiskit algorithms. Then we introduced this air simulator, which is the type of simulator that mimics the operation of a real quantum computer. That's why we do this calculation on a classical computer. That's why the number of qubits is restricted by such a small number. But it provides, but it takes into account, for example, noise, errors, and other characteristics that are unavoidable in a real simulation. Okay, we discussed the principles of unpiling, which is the process of making the circuit more feasible for the quantum computer simulation. We also discussed the single qubit golden circuit, which is essentially the opening Hadamard gate, which creates the two possibilities and the interference of these two possibilities of two states, 0 state and 1 state, right? It creates the superposition of two states. Then we have some kind of phase gate, which changes the phase of one of these states, one of these possibilities. And then the second Hadamard gate that closes up the interference. And as a result of this closing interference, it can lead to constructive or destructive interference of the resulted state. Okay, so you can constructively interfere to increase the state, the probability of the state, or destructively suppress the probability. This is very important property, essential for almost any quantum algorithm, and specifically the Grover's algorithm relies heavily on this principle of constructive destructive interference, opening and closing Hadamard gates and Hadamard gates layers. Okay, so we will start discussing this today. And finally, we discussed how we can run the quantum simulations using real quantum machines, using one of the IBM backends, right? Quantum machines. Somewhere here. Yeah, probably last time, as far as I remember, I submitted these simulations to the quantum system. So let me quickly look at the result, right? I didn't check that yet. These are 2 days. So 3 days and 5 days ago, some of you used my system to simulate the circuit. Anyways, yeah. So this is the simulation of the single qubit golden circuit, which is unpiled to this square root of x gate for this particular simulation, and this is the result. You can notice that. So this circuit is chosen to theoretically, like if the circuit would be perfect, the result will be 50-50, 50% here, 50% here. The actual result, the actual simulation, we notice this discrepancy between the two. And there was another one. This simulation, This is two qubit golden circuit. And indeed, we see that the resulting state is almost Bell state with two major states, which are 0, 0 and 1, 1, with slight addition of the state 0, 1 and 1, 0. Okay, so in the perfect case, the perfect system, we would have just only these two, 0, 0, 1, 1. For the real system, we of course have this 0, 1, 1, 0, this extra states, because of the system is real, right? Because of not perfectness of the quantum computer. All right. Yeah, so this is basically what we discussed last time. And today we transit to the discussion of quantum algorithms. So first, let me restart and clear all outputs. Okay, so first of all, I encourage you to watch this lecture 10 and 11 from my old quantum computing course, where I provide like maybe more detailed description of what I'm gonna say today. Okay, and maybe like alternative vision on the same things. So as usual, first I import the libraries, namely the Qiskit libraries we're gonna use today. And okay, I hope it works. Okay. And SymPy Quantum, which we will also probably use. So it works a little bit slow today. All right, so the quantum algorithms. There are different quantum algorithms, and there is a very extensive research work today on developing new quantum algorithms for different purposes. Okay. In our course, we will discuss only the basic quantum algorithms, but one can find like many other examples. The recent, for example, Google recently announced an award for like multi-million-dollar award for developing a quantum algorithm that can be like practically very useful if you run it on a existing quantum computer. Okay, so it's a very extensive research area today, but the most of them are based on the three main concepts. These concepts are quantum superposition, quantum entanglement, and quantum interference. Okay, so the quantum superposition, as we discussed already, and I just give you a summary, right? So suppose we have a quantum bit or qubit, which can be physical, it can be different physical system, including a photon or Josephson junction circuit or quantum dot and so on. So we can prepare, we can excite this qubit not only in the state 0 or 1, but in the superposition of these two. Meaning that if we measure the superposition, if the superposition is balanced, is perfectly balanced superposition, we can never say in which state the qubit is. It is 0 state or 1 state with some probability. And the principles of quantum physics say that we have to describe the qubit as it exists in both these states simultaneously. Okay, and this is the first principle, very important one, because this one provides the what we call quantum parallelism. Because before measurement, the qubit, we can consider the qubit being in both states, and we can do something like the computation with these both states simultaneously. And if you have a system not one qubit, but two, it's gonna be 4 states. And if our system consists of n qubits, it will be a state of 2 to the power of n states, components. Okay, so it's a colossal, huge number. And we can operate, we can compute, we can do the computation with all these states in the same time. Quantum parallelism. So next, quantum entanglement. Quantum entanglement is a concept that provides quantum parallelism, because if we bring several qubits in interaction, if we entangle them, acting on one qubit affects the other one, and this brings this quantum parallelism to life. Okay, so this is the second important principle. And finally, for the quantum algorithm, we need so-called quantum interference. Okay, so let me explain how it works. I draw this schematic circuit here. Okay, so let's suppose we have a system of M. I want to say N. So of N qubits. What we do first, usually we bring all these qubits to the balanced superposition, applying this number of Hadamard gates. Okay, so we create superposition of all these states. If it is n qubits, then it's going to be 2 to the power of n basis states. Initially, these all states are in phase. If we just close them with another layer of Hadamard gates, you will get basically what we had initially for this Q0, Q1, and so on. Let's say if they initially were in the state 0, applying the first layer of Hadamard gates, then the second layer, opening, then closing layer of Hadamard gates, and measure them, we will get just the zeros, right? In the output, it's going to be the string of of zeros. We started from 0, we ended by 0. However, if we do something like in the middle between these two layers of Hadamard gates, and I denoted this arbitrary operation by this operator f. F is some kind of function. For example, it can be this, what we call oracle or something else. And we can code or control this function. Okay, so we can use different functions. That's what I'm trying to say. And this function is realized in a way it controls the phases of every single different qubit in this array. So this function changes the states of all these qubits after the Hadamard gate. Okay, so it adds some phase. And then we close this array with second Hadamard gate layer, which leads to the constructive and destructive superposition. Okay, so for example, one can think about something like Fabry-Perot resonator. You know that if you take a slab of dielectric, like piece of glass, right, and then if you shine light on this piece of glass, because of the boundaries, the light will bounce off the boundaries and propagate like back and forth inside of this Fabry-Perot resonator, and then some light will go out. Okay, so you can say you can imagine this first layer of Hadamard gates like the first boundary, and the second layer of Hadamard gates like a second boundary. And then whatever you do between these two boundaries will affect, drastically affect the result, the light that comes out from the resonator. Something similar happens here. So we control the phases, then sum up the amplitudes. Since the amplitudes are complex, right, the result is an interference. And then we measure this interference and get the result. So the idea is that, let's say you need to do some computation, right? The idea is to create an algorithm, namely this function f, that creates the very narrow interference. Very narrow means that the result comes out from one of these output channels. Okay, so for example, C2. So I create the algorithm that changes the all phases of the qubits in a way that they sum up to create the to maximize the answer of C2. Okay, so this is the concept, more or less fair for almost any quantum algorithm. So having said this, let me transit to the quantum teleportation algorithm. And this is the first algorithm we're gonna discuss, and at the same time, the simplest one. So I want to describe this like the basic first, give some introduction, and then discuss like more practical approach to quantum algorithms. So consider this first part as a introduction, okay? And those of you who are not needed nor not interested in details, please feel free to skip this part. So when we talk about quantum teleportation algorithm, we start with the purpose. So why we need teleportation? We need teleportation because of no cloning principle. Okay, no cloning principle or even no cloning theorem states that we cannot clone the quantum state. Okay, so for example, in classical computer, for example, memory, right? The hard disk memory. The hard disk memory, you have, you record information on magnetic disk, right, in form of some pixels or voxels that are magnetized. And since this magnetization is robust or robust enough, you can using the sensor, right, the sensor of magnetic field, you can detect the state of the magnetic pixel, record it, save to another memory, or even write this this state on another hard disk, right? In quantum, it doesn't work at all, because according to the principles of quantum physics, if you measure something, if you measure the quantum state of a qubit, you destroy the quantum state. So you can't even measure, you cannot detect the initial state of the quantum system. That's why you cannot save it or you cannot clone it. In the same time, we often need to transfer the quantum state from one qubit to another qubit. So how we can transfer perfectly the state, the quantum state of a qubit from one to another one? This is why we need quantum teleportation. At this point, we always state that this is completely different meaning of word teleportation, right? You probably heard this word before, like teleport, when you, like in this how to say, in these movies, right? They kind of use it to teleport some objects, people from one place to another place. So quantum teleportation is completely different. We don't teleport any matter, it's just teleportation of the state. And moreover, and on top of that, this is the teleportation of the state via, we don't know. Okay, so we have no information about the state which we teleport. Okay, so yeah, so the quantum teleportation provides the solution to the challenge of no cloning. We need to transfer the state from one qubit to another qubit, or it can be teleportation of a state of a system of qubits to another system of qubits. That's also possible. So the quantum teleportation principle is all based on the principle of shared randomness. So you share randomness. At this point, we introduce these two guys named Alice and Bob, A and B, Alice and Bob. This is standard for the quantum computing, right? So we say that Alice has a qubit in a particular quantum state, and we assume that this state is arbitrary. So here I create the state A, which is state of Alice qubit, and this qubit is supposed to be in a superposition alpha 0 plus beta 1. Okay, so this is the state of Alice's qubit. Bob's qubit is assumed to be initially in state 0, in the ground state. So we can write using the tensor product, right? We can write the state of the system of these two qubits this way. So at this point, it is separable state, right? You can write this like 0, 1 plus times 0. So it's a separable state. This is just the way we write it. Now we create the superposition, the entanglement of the Alice's qubit with Bob's qubit using the C0 gate. Like we created the Bell states using this golden circuit. Okay, so we apply this C0 gate to this common state, and as a result, we get this shared entangled state. So now this state is entangled. As you can see, you cannot write this one as a product of two. But in contrast to the Bell state, we assume that these terms, the coefficients not equal to 1 over square root of 2. Okay, so it's some alpha and beta can be complex values. So actually, before this, now Alice wants to send her state, which is, I repeat, which is alpha times 0 plus beta times 1. She wants to send this state to Bob. They created the entangled superposition state, this one. Okay. And what Alice can do now, she can just measure her qubit. And as a result of this measurement, she can get either 0 state or state 1. If she gets 0 state, she knows that if Bob measures the qubit, his qubit, he will get 0 with 100% certainty. If she gets 1 in her measurement, the Bob will get state 1, again with 100% probability. So this is not what she wants. That's why she decided to apply the Hadamard gate. And this way, she changes the basis. Okay, she changes the measurement basis from 0, 1 state to plus minus state. Because as you remember, applying Hadamard gate to state 0 and 1 creates the superposition state, plus minus state. Okay, so she applies the Hadamard gate to her qubit and measures the qubit again. So here is the new state. So application of the Hadamard to the shared state, because of the superposition principle, right, creates this 4 states now, multiplied by alpha and beta. So now, if she measures her state and, for example, gets 0 state, there are two. So if she measures 0, she gets this term and this one, because these two terms contain 0 state of Alice's qubit, which is the first one. And these two are gone. They are not realized after the measurement. Okay, so if she measures 0, she will get this term and this term, which is perfectly what she needs, because she knows that at the Bob's side, the Bobs get the state alpha 0 plus beta 1. This is exactly the state she wanted to teleport. She might know what are alpha and beta. She might even not have no idea about what is her state, but she can teleport it using a circuit like this. So, and basically measuring the entangled system of two qubits in the plus minus basis. Okay. This is the possibility number one I listed here. However, if she measures her qubit in the state 1, so she measures her qubit and she finds the qubit in the state 1. So obviously, the Bob gets the qubit described by these two terms. So it is alpha 0 minus beta 1. This is almost the state of interest, almost the state of interest, which is different only in sign here, right? Instead of plus, he gets minus. At this point, she needs to communicate with Bob through the classical information channel and say to Bob that he needs to correct this minus, correct the sign, change minus to plus, using the Z gate, basically. This is how it works. So again, there are two options here. If she measures her qubit in state 0, she knows that Bob receives the correct quantum state. She sends state like classical 0 over the classical communication channel, like a optical fiber, to Bob, and 0 means the state he received is complete, like exactly the state she wanted to teleport. However, if she gets 1 in her experiment, she sends unit. She sends 1 over this classical channel, and Bob applies the Z gate to correct the state of his qubit. So there are two things here. First, this is the concept of shared randomness. Why shared is clear. Why randomness? Randomness because these two options, plus and minus, this 1 and 2, they come on the random basis, right? You cannot predict what you get, the possibility, the case 1 or case 2. That's why you always need to connect to Bob and let him know what he needs to do with his quantum state. This is first. So you even cannot teleport information, let's say, faster than the speed of light. This is what Einstein was scared about, right? This spooky action on distance. So it's not the case. So you can teleport a state, but you don't know the state. If you want to know what kind of the state was teleported, you still need to use the classical channel of information between two sites, Alice and Bob. And this classical channel, of course, is restricted by the speed of light. Okay. So this is the very simple description of the quantum teleportation. And let me dive now to the more practical application to quantum teleportation, which is like more standard description of quantum teleportation. And I built this one in terms of algorithm or procedure. And the procedure one, of course, is creating the qubits. Right, so we initialize the circuit. And in this case, the circuit contains 3 qubits, qubit 0, 1, and 2, and 3 classical register lines. Okay, also C0, C1, C2. So for this circuit, we need 3 qubits. So by the way, before I proceed, do you have any questions about this part, what I just described? Okay. So for more practical approach, we create the qubits. And here, what I do, I represent the state. So initially, the state of these 3 qubits written in the tensor product form is 0, 0, 0, right? So the step number 2, prepare the initial state, meaning the state of the state we need to teleport. So as an example, in this simple circuit, I want to teleport the state 1. So teleportation of state 0 is trivial, right? I want to teleport the state 1. The state 1 is created by applying the Pauli X gate to the first qubit. And I write the barriers between each single state, between the mutual states of the circuit. Okay, and this is the state of after the application of this X gate. So it is 0, 0, 1. So we changed the state of the first qubit from 0 to 1. So now I want to, or Alice wants to teleport this state, the state 1. What she does? She applies the let me say it this way. These 3 qubits, right? The qubit 0 and qubit 1 belong to Alice. Qubit 0 contains the state she wants to teleport. The qubit 1, she shares this qubit, she entangles this qubit with the Bob's qubit, which is qubit 2. Okay, so at this stage, at this state 3, Alice and Bob create the shared entangled pair of qubits, qubit 0 and qubit 1 and qubit 2. And this is the this is the state of the entire system. Okay, so next, Alice wants to measure her qubit in the plus minus basis. And to do so, she creates the superposition of, super entanglement between the qubit 0, which is the qubit that holds the state that's supposed to be teleported to Bob. Okay, so she creates the superposition between her qubits, the qubit 0, qubit 1. They belong to Alice. Then she applies the Hadamard gate to the first qubit, and this is the resulting state. Okay, so this string describes the state of all three qubits. As you can see, all of them are entangled. So it is non-separable state. So since this stage, all three qubits are entangled. And if she measures the qubit 0, that affects the state of all other qubits. Namely, the stage 5 measurements. So she measures the qubits 0 and qubit 1. So basically the qubits on her side, okay? And as a result of this measurement, she records this result to the classical register 0 and 1, here and here. As we will see, this circuit basically represents the teleportation protocol if the result of measurement is 0. Okay. However, if she measures her qubits in the state 1, she needs to apply correction. So basically, she needs to communicate with Bob, and Bob applies the correction part. So this is realized using this classically controlled Z gate and classically controlled X gate. Classically, because the control gate here, right, is not quantum, it's classical. So if Alice records 0 in the classical channel C0, then Bob doesn't apply this Z operation. Likewise, the classical channel C1, if classical register gets 0, the X gate not applied. However, if Alice measures 1 here and 1 here, then Bob needs to apply these two Z and X gates to correct the state he receives or upon this teleportation process, and he needs to correct it in a in this way. All right, so the circuit like this can be simulated, of course, using this approach we discussed last week, right? This custom simulator. This is the simulation done on my computer without sending it to the IBM. And here is the result, basically, of measuring this state, the qubit 0 and qubit 1, different statistics. Of course, the actual experiment can contain this measurement of the last qubit, of the Bob's qubit, and this is the simulation result. So indeed, this one here indicates that in all cases he gets state 1. So the state was teleported with 100% accuracy. The same holds not only for state 1, but for any other state. And let me quickly show you the result for other states even in dynamics using the platform Quark, right? So here I have multiple qubits, qubit 1, qubit 2, and we will create the qubit 3. First, I need to let's repeat what we've done using Qiskit. So I apply X gate first. This is the stage, this first stage. Second, Alice and Bob creates the entangled pair of qubits. This is done using Hadamard to the Alice and C naught between Alice and Bob. This is this part. Then Alice creates superposition between her qubits with Control X like this. And then she needs to measure her qubit in the plus minus basis. That's why she needs to apply this Hadamard gate here. and then she needs to measure her qubits, qubit 1 and qubit 2. Okay. So next, the result of this measurement must affect the state of the Bob's qubit. So let me see how we realize that. So Z gate depends on the state of the first one. Z gate that he applies depends on the state of the first one. So I apply Control Z, classical Control Z to the first one, and Control X to the second one. Where is X? X here. Control X to the second one. Okay, so let us see. So this is the state. The upper qubit is the state that that Alice wants to teleport. This block sphere indicates the state of the Bob's qubit. Okay, so let me put another block sphere here, so we see that what kind of state we have initially on the Alice side, and this is the Bob state he receives as a result of teleportation. So as you can see, completely the same, right? So now if I change the state from 0 to 1, I get the state 0 on the Alice side and state 0 on the Bob side, which is perfect, what we need. Again, state plus, state minus, minus I, plus I. So these states are the same. So it looks like the state is teleported. We can confirm that actually using the the rotation gate that rotates the state of the qubit in time. So as you can see now, this state of Alice's state, it rotates in time, but the state of the Bob's qubit is exactly the same to that one, right? Exactly the same. I can even rotate around, I can add rotation around Y and around X to make this dynamic more complex. You can see now it rotates in all 3 dimensions, and the state of the Bob's qubit is exactly the same. So the state is teleported to Bob. Of course, this measurement here and here means that the result of this measurement destroys the state of the Elias qubit and teleports it to the Bob's qubit. Okay, so after the state is teleported to Bob's side, Alice doesn't have this this initial quantum state. So teleportation leads to destroy of the quantum state we teleported. This is another important principle. Yeah, so as you can see, this is the protocol, the algorithm for the teleportation of the quantum state. The same analysis, of course, can be done using SymPy in an analytical form, right? So let me quickly go through this part. So we create a 3-qubit system. Alice's qubit is alpha 0 plus beta 1. This is the first one. Second qubit at Alice's side is in the 0 state, and Bob gets another qubit in the 0 state. Next, they entangle the second and third qubit, and this is the result of this entanglement. Then Alice creates the superposition between her qubits using the C0 gate, right? And then again transforms her basis of measurement basis to the plus minus basis, from 0, 1 to plus minus basis, using this operator here. And this is the resulting circuit. I just remind you that in SymPy, instead of going from top to bottom, we go from bottom to top, right? So this the bottom qubit belongs to Alice. And this is the state that is generated by this circuit. Okay, so if the initial state of the qubit we want to teleport is arbitrary, alpha 0 plus beta 1, so this is the most general state that is generated by this 3-qubit circuit. Okay, then we apply partial measurement to the qubit 0 and qubit 1, which are Alice's qubits, right? And we expand the result. So this is the result. As we can see, the result contains only alpha term and beta term, but it needs to correct, right? The Bob needs to correct the state to get the actual state, the actual state of the qubit, alpha 0 plus beta 1. Okay, and this correction happens or done through the classical channel. This is how the quantum teleportation works. Do you have any questions about this part? Wow. Okay, so if not, let me transit to the next topic, which is Grover's algorithm. And before we start discussing the Grover's algorithm, I need to discuss this important notation aside. Okay, so when we describe the state of a qubit or a system of qubits, we used to use this binary or standard notation, standard form, right? Like qubit 0, qubit 0, 0, qubit 0, 0, 0. And if I, for example, if I start from one single qubit in the state 0, applying Hadamard gate, it creates the balanced superposition of 2, 0 and 1. If I start from 2-qubit system of 2-qubit system 0, 0, initially, the application of Hadamard gates to 0 and 1 creates these 4 states 0, 0, 0, 1, 1, 0, 1, 1. At this point, you notice that these terms 0, 0, for example, it is 1 in the integer form, right? So, for example, if you likewise for the second term 0, 1, this is the second integer number. 1, 0, this is third number, and so on. So we will see that we can use this integer format of presentation of the state of a qubit using the integer format, the numbers 1, 0, 2, and so on. And that's actually more like useful for theoretical approach and for calculations. Likewise, for a system of 3 qubits, if I apply the Hadamard gates to all of these 3 qubits, right? This is the resulting state. How many terms here? 2 to the power of 3, which is 8. 8 states. So this is the balanced superposition state of a system of 3 qubits. Like if we go back to this point of C. So right, we describe now this part of the circuit, applying the Hadamard gate to every single qubit creates this superposition state of 2 to the power of n elements. For 3 qubits, this is 8 elements like this. And we have all of them, all possible basis states, 0, 0, 0, 0, 0, 1, and so on. So 8 of them. For a system of 100 qubits, we would get the line like this with the number of terms of 2 to the power of 100, which is a huge number. Also, as you can see, if we add more and more qubits to the system, the number of terms grows extensively, exponentially, and it's not feasible for writing these states, right? So how we can numerate them, how we can write like summations of them. So that's why a better way to represent the states of the qubits using the integer format. So for example, from SymPy Quantum, you can import this integer qubit operation, and the same part like this can be now written in a more appropriate way in the integer format, right? So now we have not 0 and 1 states, but also 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, and so on states, right? So 8 terms in this line, starting from 0 to 1, because we always count qubits from qubit 0 to qubit n minus 1. So if I write the state, the general superposition state of a system of n qubits, n capital qubits, which means n, which means 2 to the power of n possible states, right? So n is the number of states. I can write this superposition in this form, right? So here, sorry, this superposition, the binary format, the binary format like this can be written in this form. So here, this vector x, b stands for binary, means that you write the state using zeros and ones and sum up for all possible combinations of zeros and ones of dimension n. Okay, so you just write all possible zeros and ones that fit to this dimension n. For example, for the system of 3 qubits, this is what I mean, writing all possible combinations. 3 zeros, 2 zeros and 1, 0, 1, 0, 0, 1, 1, and so on. All the combinations of all these zeros and ones. Likewise, if I use this integer qubit approach, I can write exactly the same state in a more in a more feasible way. So now I don't want to write all possible combinations of zeros and ones. I just write the summation over this state xi, which is basically just the digital number, right, or integer number from 0 to n minus 1. So it's summation of state 1, state 2, state 0, state 1, state 2, and so on. And this is important because using this approach of writing this integer qubits, we can draw something like this. Let me come back to this circuit here, right? So here we have this first layer of opening layer of Hadamard gates. The same part of the circuit now can be written using this notation. This one line here means not only one qubit, but if you see this inclined line like this with the index n, it means that this is a group of qubits of dimension n. So n qubits. Likewise, application of these Hadamard gates, instead of writing all these Hadamard gates, you can just write h to the power of tensor product n. So it means just creation the first layer of Hadamard gates for the superposition. And as a result of this circuit, this state S, which is perfect superposition of all basis states written in the integer form and binary form. One can use both forms, like depending on when one and another one more preferable. So having said this, let me start the discussion of the Grover's search algorithm and how it works in a simple form, in a simple way. Here is some information about Grover's algorithm when it was proposed. You see, even like well before the actual quantum computer was actually built, right? At this time, the most successful experiments were only creation of a system of two entangled qubits. Okay, so it's not even a computer, it's just some first experiments with quantum entanglement, superposition and entanglement. Yet, even at that time, people already believe that at some point we will create the computer to run these algorithms, and using modern quantum computers, we can run the search algorithms. Another point is that it makes sense to use Grover's algorithm for a very large number of qubits. Okay, so I would say today's quantum computers are not sufficiently large in terms of number of qubits to do something like practically useful. But still, we develop to that point. So Grover search algorithm is about search of a particular element in a non-structurized list of elements. These elements can be, for example, words, numbers. It can be like phone numbers, some other elements, just non-structured list of elements. Okay, you know the element you after, you looking for, of course. You just don't know where this element located. Okay, like on the internet, you search for some specific item, and you know exactly what you're looking for, or more or less, but you don't know where this element is located. Okay, and the classical algorithm for solving this problem says that we need at least n evaluations to locate the element we looking for. At least n tries. For example, this blind search will require, in average, exactly like the number of tries, number of calls to the list of about n. The quantum Grover's algorithm provides the quadratic speedup, meaning that the number of calls to the list of elements will scale up as square root of n. So instead of, for example, 100 calls, you will need to do like 10. Or instead of 10 to the power of 4, like 10,000 elements, you will need to call just 100 times. So for a list of a small number of elements, the algorithm is useless, right? Because n and square root of n not that much difference. However, if n is a very large number, then the algorithm provides a great speed up to the work. So the principle of this algorithm I formulated here. So we encode the list of elements, again, words, numbers, whatever, into the quantum state of a sufficiently large number of qubits. So ideally, if your list contains like billion of elements, ideally we need to have a system of like billion qubits. Well, it can be also billion quantum states. It can be a system of quantum states. So not billion, but still a lot of sufficient number of qubits. Okay, so you encode this list to the states of the quantum machine, and then the Grover's algorithm is applied to constructively interfere. This is what I meant up here. So we apply this Grover's algorithm to provide the constructive element for only one single like output. For example, we search for this element C2 in the list. So the Grover's algorithm increases, like constructively increases through constructive interference. It increases the probability of C2 and destructively suppresses the other outcomes. So this is the idea. And let me quickly discuss how actually it works. Okay. So we know the element we are looking for, some element omega, for example. We encode that element into the state of a quantum computer, and we denote this state omega here, this ket vector omega. So this is the vector we looking for this state. We're looking for the element. We know the element. We know the we know the element, but we don't know where the element is located in the list. Okay. So we know this vector, and we can find the orthogonal vector to this vector omega. We can easily find the orthogonal vector S, right? So this vector S is vector orthogonal to the vector omega. So what we do? We create the perfect superposition of superposition state, this kind of state, or this one, which is exactly the same. So the perfect superposition state using the number of Hadamard gates. So we apply Hadamard gate to every single qubit to create the state S, the superposition state. This is the state S here. We know this state, of course. This is just the superposition state. What we do next, this is written here. So what we do next, we rotate this vector S by some angle, which we name angle theta over 2, half theta angle, around this vector S prime. So this is just described here. So we rotate this vector or reflect this vector across the this vector S prime. And the result is U omega S, U omega vector S. This U omega is some unitary operator, of course, because all transformations in quantum computing are unitary, except for measurement gate, which is not actual gate. It's just the element we used to measure it. This from classical physics. And square root of x is another example of non-unitary operator, but applying 2 square root of x is a unitary operator. So this U omega, sorry, is a unitary operator that creates another vector here, and this vector essentially is a result of rotation of vector S around vector S prime, which is, I remind you, orthogonal to the state omega. Orthogonal to the state omega. Second, we apply another operator to this new one. We call this operator US here to rotate this vector u omega s around the vector s, this vector superposition state vector, again, I remind you, created by the number of Hadamard gates we applied to the qubits. Okay, so we rotate this gray vector around vector s, and the result is this new vector us u omega s. So this is the result of these two operations. This is called Groover's operation, if you wish. U omega is called oracle, okay, because we designed this operator depending on the state we after. So we designed this operator somehow. The operator US is called amplifier for the reason that's gonna be clear in what follows. So applying this oracle and amplifier, you see that the result from this vector s, you get the new vector us u omega s, right? And this vector is rotated closer to the state we after, to the state we looking for. Okay, if we repeat this operation us u omega, we will get another vector which will be rotated closer to the omega. If we repeat it again, we will get another one which will be yet closer to the state omega. So we apply this operation us u omega the sufficient number of time to get our vector s, initial vector s, close to vector omega. And Groover claimed that this can be done in the less, basically it can be done using just square root of n iterations. Okay, so it is one run of circuit, one run of algorithm, but you apply Groover's iteration a sufficient number of time. So this pair, this u omega us, is called Groover's iteration or Groover's pair, if you wish. The number of application of this Groover's iteration, as we will see next week, is defined by basically square root of n. Okay, that's why the scales are square root of n. Yeah, and this is the schematic like circuit of this algorithm. Let me repeat. We start from a number of qubits n initially in the state 0. Then we apply the opening layer of Hadamard gates. We create the superposition. Then we apply the Groover's iteration pair, which consists of the oracle and the amplifier. And amplifier, as you see, amplifier means we amplify some some terms, some amplitudes, the probability amplitudes of the element we are looking for, and suppress the amplitudes of all other elements. Okay, that's why basically it is amplifier. Yeah, and then we do the measurement. We don't need to close the interference now because the state we after already is the state of the maximum probability, right? So this Groover saturation pair already works to provide the strongest interference, strongest amplification to the state we're looking for. So, and here, just let me go very quick. I will discuss this next week. The Qiskit example of the Grover's algorithm. So for in this example, which is not trivial, let's say, it's because the other sample examples with 2 qubits, they are rather trivial. So this one is less trivial, but at the same time, like more complex for the analysis. So we create a circuit of 3 qubits and a number of classical registers. We create the perfect balanced superposition state by applying the Hadamard gates, this layer of Hadamard gates. The result of this is this vector S here, this vector S. Okay. And in this particular example, we will look for 2 states, state 101 and state 110, just 2 arbitrary states. As you can see, we can not only look for one element, we can look for example, 2 elements. So this also can be done with Grover's algorithm. To do so, we create the phase oracle. And for this circuit, for this task, 010 and 110, the oracle is just swap these 2 swap gates. Okay. We will discuss this next week. This is just to show you how the actual oracle can look like. And then we apply so this is the oracle, right? And then we apply this part. So I would say the oracle is actually this part here. This is oracle. We designed this oracle to search for a particular element or 2 particular elements in our list. And our list consists of 8, just 8 elements now. So it's, again, rather useless, but demonstrates nicely the idea of this algorithm. And this part is the amplifier. So this is how the amplifier looks like. So the amplifier is pretty much the same for any circuit. Amplifier is the same or differs just a little. Oracle is designed for each particular element. Again, I emphasize that these gates, they are not physical, right? You don't need to like physically create the circuit like this when you design the oracle. You don't need to solder new elements there, change your circuit. No, these gates are stimuli, and finding the appropriate oracle means just changing the pulses, just pulses, their duration and consequence, okay, of the pulses. So don't be like confused that we design the oracle and this oracle changes the circuit. There is no physical change of the circuit because this quantum circuit is not spatial, is temporal, right? So it's just the matter of pulse design. That's it. And for every element, this oracle can be designed. All right, and yeah, and then we measure. So we apply this closing Hadamard gate level layer. In this case, it is a part of the circuit, but I guess you can work even without this layer. And then three measurement gates to measure the qubits. And this is the result. So indeed, in this classic quantum simulator using classic machine, the result is here, right? So we've got basically two answers, state 101 and state 110, with more or less 50% probability. This is the this was our task, right? To find exactly these states. Yeah, so this is how it works in simulations, in theory. Next week we will delve in more details to Grover's algorithm, and we'll discuss other algorithms as well. So do you have any questions about this part? Okay, if no, let me stop the recording and we can discuss maybe our course things. Let me stop, yeah.